When you use a consumer AI tool, you interact with a closed system. You type a prompt into an empty box, and seconds later, an answer appears. It is a sealed, autonomous loop. Drop that same sealed loop into an enterprise environment, and it breaks. Corporate infrastructure requires strict data governance, active security audits, and real-time integration across legacy platforms. A standalone wrapper cannot fulfill those requirements. The core engineering challenge lies in bridging two entirely different types of computing. Large language models are probabilistic reasoning engines. They guess the next most likely word based on patterns. Enterprise systems like SQL databases are rigidly deterministic. They require exact predefined commands to function. To see how these systems integrate, looking at a static architecture chart is insufficient. We have to trace the hidden journey of a single user query as it dynamically moves across the entire application stack. True enterprise AI operates as a heavily layered orchestration ecosystem. The language model itself is merely one small, isolated component buried deep within the stack. A business user types a prompt into a dashboard, generate a monthly sales analysis report, and identify top-performing regions. That text string becomes a data payload. To return an actionable answer, it must traverse 8 distinct architectural layers. The journey begins at the application front end. This presentation layer relies on standard web frameworks, completely separate from the AI infrastructure. At this initial stage, the process operates exactly like a standard HTTP request. The front end submits the text and waits for the back end to validate the session. While the end user experiences a simple chat interface, beneath the surface, a massive, highly regulated state machine has just been activated. The payload strikes the API gateway layer. It queries the identity provider, verifying multi-factor authentication. Next, role-based access control ensures this user has rights to query regional sales. Finally, the prompt undergoes data masking, replacing restricted parameters with redacted tags. The gateway also applies rate-limiting protocols to this request, tracking API usage to control compute costs and prevent denial of service overloads. This deterministic security wall is absolute, existing precisely to guarantee that probabilistic AI models cannot accidentally bypass corporate compliance protocols. The validated masked payload enters the core application layer and is handed off to the AI orchestration engine. This engine does not generate natural language text. It functions strictly as a planning and routing mechanism to manage the workflow. Mapping the agent framework, the payload hits a master agent, splitting into discrete tasks. It routes quantitative queries to a data agent built for traditional databases. Simultaneously, it delegates visualization to a reporting agent, preparing a blank dashboard template. Automatically decomposing the prompt into specialized tasks prevents a single language model from hallucinating under the weight of complex, multi-step instructions. Tracking the data agent, we see it execute rigid SQL queries against the enterprise data storage layer, retrieving a structured table of hard revenue figures. Raw metrics lack context. For accurate narrative analysis, the system needs proprietary business context. Entering the RAG pipeline, the text prompt is converted into a mathematical vector. A semantic search aligns this vector against an enterprise database, extracting the most relevant prior reports. Inside the prompt builder, the hard SQL metrics and the retrieved document text are merged. This is context injection. Foundational language models possess no inherent knowledge of internal operations. Accurate answers emerge because the RAG layer explicitly injects verified corporate context into the prompt prior to LLM activation. The heavily structured, context-rich prompt finally leaves the secure enterprise boundary, reaching the external large language model service. At this moment, the external LLM is completely blind to the underlying enterprise architecture. It only sees the specific masked data payload that was injected. The model executes its reasoning function. It processes the injected data, generating narrative analytical insights, and writing the specific SQL code to render the final visualization. The completed response payload re-enters the orchestration engine, caught by the reporting agent. It pushes this processed code into the business integrations layer. Targeting Power BI, it instantly renders a visual bar chart and formats an executive summary. The value of the AI integration relies entirely on the deterministic execution of the model's text into a secure, actionable enterprise dashboard. Zooming out, we can see the full architecture map. This is the exact zigzagging path a single user query takes across the gateway, the agents, the RAG pipeline, the LLM, and the BI integrations. An invisible monitoring and governance layer silently records every millisecond. Because every stage, from the initial SQL query to semantic RAG injection, is cross-referenced against corporate data, the architecture eliminates LLM hallucinations. This rigorous verification allows organizations to consistently hit accuracy targets over 95%. Maintaining strict component separation allows administrators to track API costs per query accurately and isolate the root cause of any system failures. A single isolated query proves the mechanics, but the architecture is designed to scale horizontally across the entire organization. By standardizing the routing and governance layers, an organization can move beyond isolated applications to build a comprehensive enterprise copilot ecosystem. This framework allows specialized, distinct assistants for HR, finance, IT, and operations to operate simultaneously, all safely pulling context from a unified enterprise knowledge hub. By automating the hours spent on manual SQL coding, document synthesis, and report formatting, this 8-layer journey effectively replaces the most tedious parts of the analytical workflow. In practice, this architectural shift results in a 60 to 80% reduction in manual reporting effort. Integrating language models requires building a secure, multi-layered nervous system capable of executing intelligent logic at an enterprise scale.